Numerical number 1. A uniformly charged metallic sphere has a total charge of 300 microcoulomb and a radius of 8 centimeter. Radius is given 8 centimeter and the total charge on the sphere is 300 microcoulomb. Now since it is a metallic sphere, the charge will be on the surface of the sphere. Find electric field intensity at a point where distance from the center of the sphere is 16 centimeter, 8 centimeter and 4 centimeter. So first, let us find out electric field at distance 16 centimeter from the center of the sphere. The formula that can be used here is E is equal to K Q upon R square. K is 9 into 10 raised to 9. Charge is given 300 microcoulomb. So we have to convert that into coulomb. 300 into 10 raised to minus 6 upon distance from the center of the sphere. First we need to take 16 centimeter. So 16 into 10 raised to minus 2 whole square. On simplifying this, we get the answer 1.05 into 10 raised to 8 Newton per coulomb. Part B. Electric field intensity at distance 8 centimeter from the center of the sphere, that is nothing but the surface of the sphere. So formula again remains the same. E is equal to KQ by R square. K is 9 into 10 raised to 9. Charge 300 microcoulomb. And distance is 8 centimeter. So 8 into 10 raised to minus 2 whole square. On simplifying this, we get the answer 4.21 into 10 raised to 8 Newton per coulomb. And in part C, we need to find out electric field at distance 4 centimeter. So at a point 4 centimeter distance from the center, there is no electric field, right? Because we know that there is no electric field inside the sphere. So answer of part C is 0. Numerical number 2. A charged conductor has surface charge density of 1 into 10 raised to minus 7 coulomb per meter square. What is electric field intensity just outside its surface? So here the formula is E is equal to sigma upon epsilon 0, where sigma is surface charge density. Its value is given to us 10 raised to minus 7 and epsilon 0 value we know 8.854 into 10 raised to minus 12. On simplifying this, we get 1.13 into 10 raised to 4 Newton per coulomb. Numerical number 3. Careful measurement of electric field at the surface of a black box indicates that the net outward flux through the surface of the box is 8 into 10 raised to 3 Newton meter square per coulomb. What is the net charge inside the box? Alright, so here what we are given is the flux value. And we know that flux is equal to Q upon epsilon 0. So using this formula, we can easily find out what is the net charge inside the box. Let us substitute the values. Flux is 8 into 10 raised to 3. Charge we want to find out, and epsilon 0 we know 8.854 into 10 raised to minus 12. So the charge value here comes out is Q is equal to 70.83 into 10 raised to minus 9 coulomb. Next is, if the net outward flux through the surface of the box were 0, what can you conclude about the charge inside the box? So again, if I use this formula, phi is equal to Q upon epsilon 0, for phi to be 0, okay, for phi to be 0, Q must be 0. Charge becomes 0 under two conditions. First, when there is no charge at all, or the second is charge is the net charge. Here the charge is net charge, so that must be Q1 minus Q2. So if Q1 is positive and Q2 is negative and both are having the same magnitude, then Q1 minus Q2 becomes 0. Numerical number 4. A conducting sphere of radius 0.1 meter has an unknown charge. If the electric field at a point 0.20 from the center of the sphere is 1.5 into 10 raised to 3 Newton per coulomb and it is pointing radially inward, calculate the net charge on the sphere. So to find out the net charge on the sphere, we can use E is equal to KQ by R square. Electric field intensity value is given. So let us substitute all the values which are given here. So 1.5 into 10 raised to 3 is equal to 9 into 10 raised to 9 into Q upon distance is 0.2 meter. So 0.2 square. So we get Q as 6.6 into 10 raised to minus 9 coulomb. Okay, or we can say 6.6 nanocoulomb. But here see that the electric field is pointing radially inward, and that happens only if the charge on the sphere is negative. Okay, because if charge on the sphere is negative, then the electric field lines will be pointing towards the sphere. That is why the answer of Q must be minus 6.6 nanocoulomb. In second part, we need to find out electric flux through the sphere. So the formula is phi is equal to Q inside upon epsilon 0. On substituting the values of Q and epsilon 0, that is 6.6 into 10 raised to minus 9 coulomb upon epsilon 0. On simplifying this, we get minus 7.5 into 10 raised to 2 Newton meter square per coulomb. Numerical number 5. Consider a uniform electric field E is equal to 3 into 10 raised to 3 I cap Newton per coulomb. Electric field is along x direction. Okay, so let's say these are coordinates x, y, z, and electric field is pointing towards positive x direction. What is the flux of the electric field through a square of 10 centimeter on side whose plane is parallel to yz plane? So we need to draw a plane which is parallel to yz plane, and electric field is pointing towards x direction. So here we will consider area vector also along the same direction of electric field. So we can easily use the formula for the flux now as phi is equal to EA. E is 3 into 10 raised to 3 and area will be 10 into 10 raised to minus 2 whole square. Okay, converting centimeter to meter. The answer is 30 Newton meter square upon coulomb. And in part B, we need to find out what is the flux through the same square if the normal to the plane of the square makes an angle 60 degree with the x-axis. So here we have to use the formula phi is equal to EA cos theta. EA value we already know, that is 30 cos 60. Cos 60 is half. So 30 by 2, that is 15 Newton meter square per coulomb. Sixth numerical. A point charge causes an electric flux of minus 1.0 into 10 raised to 3 Newton meter square per coulomb to pass through the spherical surface of 10 centimeter radius centered on the charge. So we are given a sphere, radius of the sphere is 10 centimeter and the charge is at the center of the sphere. Now here the flux value is minus 1.0 into 10 raised to 3. That means the electric field values are pointing towards the sphere. And since the electric field lines are pointing towards the center, the charge at the center must be negative. Flux is minus 1.0 into 10 raised to 3. Now here the question is, if the radius of the Gaussian surface was doubled, how much flux would pass through the surface? So if we draw the Gaussian surface of radius 20 centimeter, the charge enclosed within that particular Gaussian surface remains the same as the earlier, that is minus Q. Now since the charge is not changing, the flux value will also not change. So the answer of sub question A here is no change. Now in part B, we need to find out what is the value of the point charge. So we can use a very simple formula, phi is equal to Q inside upon epsilon 0. So Q is minus 1.0 into 10 raised to 3 into 8.854 into 10 raised to minus 12. That is minus 8.854 into 10 raised to minus 9 coulomb. Seventh, a uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of 80 microcoulomb per meter square. So we are given the surface charge density, that is sigma 80 microcoulomb per meter square. Find the charge on the sphere. So the formula to be used is Q is equal to sigma into area. Sigma is 80 microcoulomb, 80 into 10 raised to minus 6. Area is 4 pi r square, 4 pi Radius will be 1.2 meter. So the answer is 1.45 into 10 raised to minus 3 coulomb. In part B, what is the total electric flux leaving the surface of the sphere? So the flux is Q upon epsilon 0. Q 1.45 into 10 raised to minus 3, and epsilon 0 value we know. So the flux becomes 0.163 into 10 raised to 9 Newton per meter per coulomb. Eighth, a point charge of 17.7 microcoulomb is located at the center of the cube of side 0.3 meter. Find the electric flux through each phase of the cube. So let us first find out the total electric flux, that is phi is equal to Q upon epsilon 0. 17.7 microcoulomb, so 17.7 into 10 raised to minus 6 upon epsilon 0, 8.85 into 10 raised to minus 12. Now this value is the total flux, meaning the flux coming out of all the surfaces of the cube. But here in the question we need to find out the flux only through a particular surface or through each surface. So the flux coming out from each surface will be 1/6 of the total flux. So 1 by 6 into 17.7 into 10 raised to minus 6 upon epsilon 0 value, and this is 3.33 into 10 raised to 6 Newton meter square per coulomb. Ninth, the flux of electrostatic field through the closed spherical surface S dash is found to be 4 times that through the closed surface S. So flux through S dash is 4 times flux through the surface S. Find the magnitude of the charge Q. Alright, now if you find out the total charge enclosed by the surface S dash, that will be Q1 plus Q2 plus Q3 plus capital Q, which we want to find out. So the flux passing through the surface S dash will be Q1 plus Q2 plus Q3 plus capital Q upon epsilon 0. And this is 4 times the flux of the surface S, and the charge enclosed by the surface S is only Q1, Q2 and Q3. So this is 4 times Q1 plus Q2 plus Q3 upon epsilon 0. Values of Q1, Q2, Q3 are given, so let us substitute. Q1 is 1 microcoulomb, Q2 is minus 2 microcoulomb, and Q3 is plus 9.84 microcoulomb. So on simplifying this, we get Q as 26.52 microcoulomb. 10th, in the figure shown below, calculate the total flux of the electrostatic field through the spheres S1 and S2. The wire AB shown here as a linear charge density lambda, and lambda is given by Kx. Okay, so first if you look at the figure, to find out the electric flux through the surface S1, we can use the formula phi 1 is equal to Q, that is the charge inside the surface S1 upon epsilon 0. Okay, so this is the flux passing through the surface S1. Now to find out the flux passing through the surface S2, we can use the formula phi 2 is equal to Q inside the surface S2 upon epsilon 0. Now this Q inside the surface S2 will be of course Q, that is the charge inside the sphere S1 plus charge on the line AB. So now we need to find out what is the charge on the line AB first. So to find out the charge on the line AB, we have to use this fact that total charge on the line is equal to integration over dq. What is dq? Suppose if I take this wire AB and divide this wire into small parts, then the charge on the smallest part, that is on line element DL, is dq. So likewise, if we divide this entire wire into small line segments, find out dq of each line segment and then add them. So ultimately what we are supposed to do? We are supposed to integrate. So q is equal to integration dq. But this integration dq will be lambda into dl. Okay, we are using the fact that linear charge density lambda is total charge per unit length. So instead of writing q by L, we can also write dq upon dl. So q becomes integration lambda dl. Instead of dl, let us use dx. So now putting the value of lambda, we get integration kx dx. K is constant, integration x dx is x square by 2. And if you put the limits of the integration, that is 0 to L, our answer is k is equal to k L square by 2. So when we substitute this value here in the formula of phi 2, we get phi 2 is equal to q plus k L square by 2 upon epsilon 0. This is the answer for flux passing through the surface S2. Thank you.